Hello, YouTube. We started. Apologies for starting in medias res here, because I forgot to hit the record button because I haven't done this for a week and a half. Anyway, so we were just reviewing the 5 facts about finite fields, and I think we were ready. We're ready to move on. Yes, everybody says we're ready to move on. So let's do that. Oh, right, because I want to do a concrete example. So computing in F16. So as we just said, I think. Oh yeah, I think before break I should mention that we were going to prove the uniqueness here. That I thought, but I thought about it. And I thought, well, it's probably better to move on because there aren't that many problems about finite fields. And so, but I did want to actually show you something concrete, which is actually more. This is actually kind of more like my other course. Applied in industrial algebra, but this is so I find this so useful to think about, like, what actually is F16, that I can't resist doing this one, at least one example concretely. Okay, so it is a fact that the polynomial m of x equals x to the fourth plus x plus 1 is irreducible over F2. So let alpha be a root of m of x, or in other words, let form the field F2 of alpha, join alpha, and which is isomorphic to F2 bracket x mod m of x, and that and the point is that because 16 is equal to 2 to the 4, then m has degree 4. M has degree 4, that means that this field must have order 16, and must therefore, by that uniqueness theorem, must actually be the field, or at least isomorphic to the field of order 16. And so the question arises, how do you actually compute in this field? Like, how do you write down elements? Well, you may remember that because when you write down an element, when you work, so mod m. So I'm gonna in a minute write down the 2 random elements of F16, because the point is, what mod m of x, you end up that what happens is that because m of x has degree 4, then sort of mod m of x, all polynomials have degree 3 or less. So we end up with things of degree less than or equal to 3. And so if alpha is a root of m of x, then the point is that every element of F16 can be expressed uniquely as a polynomial in alpha of degree less than or equal to 3. Let's see. So in the chat, can somebody just type in type in some subset of the set 0 through 3 just quickly? Just 2 people do that. Okay, so Trent says 1, 3. So alpha cubed plus alpha. And so we'll let beta be alpha cubed plus alpha. And someone else, give me some subset of the set 0, 1, 2, 3. Zero, 2. Okay. So Carlos says 0, 2. And so, all right. And so we will somewhat randomly pick gamma equals alpha squared plus 1. Thank you for only picking binomials, which makes this go a little faster. So now, okay. So what I want, and although actually I'm going to make this just a tiny bit more complicated. Oops, I wanted to hit the eraser there. I'm going to just make this just a tiny bit more complicated by adding alpha plus 1 here. Sorry, Carlos. Because this will sort of, because I need to do that in order sort of to illustrate addition. So now what I want to do is I want to compute beta plus gamma and then beta times gamma. Well, Amy, so let me actually sort of do this, and then you'll see that the point is that that addition is easy, and I think and we have kind of discussed this before, but multiplication is slightly more complicated, but can be made sort of more practical using a reduction rule. Anyway, so so first, when you add beta plus gamma, you get alpha cubed plus alpha plus alpha squared plus alpha plus 1. And now one interesting, the one interesting thing that happens here, the reason I wanted to add in that alpha is that we see that these two terms added together give you 2 alpha. And so, and the thing is 2 alpha, so this field is still characteristic 2, and which means that 2 alpha is still equal to 0. So what happens is basically when you add elements of F16 written in this form, then all you're doing is you're adding ordinary polynomials, but there's still ordinary polynomials with coefficients mod 2, and so those two things cancel out, and so you get alpha cubed plus alpha squared plus 1. So everybody good with that so far? All right. Okay. So the multiplication is where things get a little more interesting. So the thing I feel like I've done this before, but never mind. I'm just going to do it again because probably this is because it took me so long. Oops. To learn this that I feel like I want to keep repeating it. So so again, if when we're working mod m of x, when we have mod m of x, we have that alpha to the 4th plus alpha plus 1 equals 0. So that's, again, that's what it means to sort of be working mod m of x. And the idea is that alpha is the image of x in this quotient ring. And so when you plug that into the m of x, that by definition has to be equal to 0. And so we're really doing is setting alpha to the 4th plus alpha plus 1 equals 0. But since but the sort of more useful way to think about this is that alpha to the 4th is equal to alpha plus 1, where of course minus is equal to plus because we're working characteristic 2. So I hope that sounds familiar, right? So we're now going to apply the rule that alpha to the 4th is equal to alpha plus 1. Everybody good with that? Say yes in the chat. Or ask a question. Okay, so then the point is, what happens is when you multiply these two elements, beta times gamma, you start off by using essentially ordinary polynomial multiplication. So you get, let's see, alpha cubed times alpha squared plus alpha plus 1 is, oops, let me use the mouse here, alpha to the 5th, so plus alpha to the 4th plus alpha cubed. And now when I add the, when I do the alpha times these guys term, I get another alpha cubed. Oops, I say another alpha cubed, there it is, plus alpha squared plus alpha. And so this is equal to, and so again, we have this thing where this phenomenon, because we're working characteristic 2, that these two terms cancel out, and then we get alpha to the 5th plus alpha to the 4th plus alpha squared plus alpha. But again, okay, so that's so far just ordinary polynomial multiplication. But what we said before is that what we want to do, our final goal is to express everything as in terms of polynomials in alpha of degrees less than or equal to 3. And we see over here that the way to do that is we use the reduction rule alpha to the 4th equals alpha plus 1, but also alpha to the 5th equals alpha squared plus alpha, which we get by multiplying the previous reduction rule by oops, where did my cursor go? The previous reduction rule by alpha. Uh-oh. Oh, there's my cursor. How do I get over there? There's a better looking 5. All right. So Yeah, anyway, so so now that we have those two reduction rules, if I can ever get the eraser to show up here. All right, so there we go. Now, so continuing, we see that alpha to the 5 is equal to alpha squared plus alpha, and alpha to the 4th is equal to alpha plus 1. And they already, oh, look, we already had an alpha squared plus alpha sitting here. So conveniently, those two terms cancel out completely, and we're left with, oops, slightly not quite the color I intended, but fine, alpha plus 1. Okay, so yeah, beta times gamma is alpha plus 1. So I know I've done this before, but that's okay. A little repetition is the mother of belief. Repetition is the mother of belief. Repetition is the mother of belief. So are we good? And so okay, a question from Ravi. So when f is a field and m of x is a polynomial, then f of x mod m is the same as so Ravi asked that when f is a field and m of x is a polynomial, then f of x mod m is the same as adjoining every root of m to f, any root of m to f of x. Yes, as long as m is irreducible. Right, it would be weird. Yeah, as long as m is irreducible. Yeah, so that it is important. Irreducibility is important for that fact to hold, but that did not help at all. Oh my goodness. Let's try that with my finger. There. Okay. Yeah. So as long as m of x is irreducible, that is correct. So as long as m is irreducible, then adjoining a root of m is exactly the same as taking polynomials and modding out by m. But yeah, other than that one technical point, that's true. All right. So everybody good? Okay. So oh right. So and I left the space. So does anyone have any questions about chapter 15 or problem set 7 or the practice exam? So I remember our one sort of boundary that we set is that the take home is not to be done collaboratively or with help from other folks. But I'm happy to answer questions about chapter 15 or problem set 7 or the practice exam. So anybody got anything there they want to get off their chests? By the way, I'm still trying to get somebody to be the guest DJ no, not the guest DJ, but the DJ for the day who's not me. I'm really curious to see what everybody else is listening to in music. I might just sort of pick somebody and ask you to do it individually. I'm determined to make this work. I'm determined to make fetch work. Fetch? Mean Girls? No. Right. Maybe you're reacting. I'm sure you're all laughing uproariously at home. Yes, that's right. Thank you, Trent. You get it, even if I'm even if I'm not delivering it correctly. Okay, but so no questions. So we should no questions. Move on. All right. So hopefully this is all working out. And if you have questions that you want to ask privately, please, of course, go ahead and do so. Or if you want to ask it this in sort of a more relaxed fashion, you can always ask them on the Piazza board. So let's move on to oh right, but before we get to chapter 16, there's something I forgot that we had to do in chapter 15 that does pop up. It doesn't pop up in I think it doesn't really pop up in the calculations so much as it's a sort of useful technical tool for proofs. For proofs in chapter 16. And that's the following thing. So if you have, so that says if the characteristic of f is 0 and k mod f is finite, so if you have a finite extension of a field of characteristic 0, then it is a fact that k is always equal to f adjoin a single element alpha for some alpha in k. And alphas, and we call alpha a primitive element for k, the extension k over f. So in practice, actually, you kind of see in practice you wouldn't actually want to do this in practice for calculations, as we'll see later on. The calculations usually use something a little more symmetric looking, or sort of more natural. For proofs, it's convenient to be able to say, well, just be able to say like, well, you know, if you have a finite extension k over f, well, just suppose let alpha be a primitive element of that extension, and then go from there. So the idea of the proof is that we know, just sort of by induction on the degree, that so the idea of the proof. Let's see if we can remember how to type. This is another thing I have to remember. Oh, look, it's still blue. So since any finite extension. Yes, I forgot that. Now I've really, oh, good. I can remember how to do the most difficult thing, which is extend this box somehow. Since any finite extension is obtained by adjoining finite list of elements, it's enough to show. Okay, there's my first box extension failure. It's enough to show, right? So you know, since it's enough to show that you can reduce an extension by 2 elements to an extension by 1 element, because then later on, because then, you know, sort of applying that finitely many times, you combine like your 77 elements that you added into a single element. And the point is that basically, if you take some random, what this essentially says is if you take some random element, random linear combination of alpha and beta, that will actually be equal to extending by both alpha and beta. So and you know, and there's some a little bit of cleverness involved in getting that, but you know, that's the basic idea. Is that if you take just a random linear combination of any 2 elements, you'll get 1 element that generates the extension of both of them. So I just want to point out that you would, so in practice, the reason that you wouldn't want to use the primitive element in practice is that the primitive element in practice would look something like, well, if you wanted, so that is if you had you know, this alpha is going to be equal to, like, you know, alpha 1 plus C2 alpha 2. It'll look like some kind of random. I guess what this is really saying is that if you get a finite extension by adjoining finitely many elements, then and you take essentially a random linear combination of those elements, then that adjoining that single element will actually have the same effect as adjoining all of them one at a time, which is, I guess, it's nice to know. But the fact that you sort of have to take a kind of random linear combination of elements makes this actually much more unpleasant computationally, whereas in practice we'll see that for Galois theory, that you actually want to just look at them one at a time. That's actually more helpful. Oh well. Anyway, so that's what the primitive element looks like in practice. Okay. So really, again, this is just a more of a technical tool for the sake of doing proof, making your proofs shorter. You can all start your proof by saying, well, suppose I obtain my finite extension by adding a single element, then yada yada. All right. So is everybody good with? Anyway, I bet I can draw a square here somewhere. Yeah, too risky. All right. So is everybody good with this theorem now? I really wonder what these awkward pauses look like. I have to actually watch one of these videos and see what these awkward pauses look like on YouTube. Okay, so now we're on to chapter 16, Galois theory. Yay! Chapter 16, and that will take us to the end of the semester. Yeah. And, and I think we'll all be grateful to get to the end of the semester. I've really enjoyed this class. You guys have been great to teach, but I think we'll all be relieved to get this semester done. But I'm sure we'll look back on this time fondly. Anyway, so here's Galois theory in a nutshell, and I actually try to bring this slide up pretty much every class for the rest of the year. For the rest of the year, right? So suppose the extension k of f is the splitting field of a polynomial little f of x in big F bracket x, or in other words, little f of x, a polynomial with coefficients in the base field capital F. I guess we should be honest here and just go ahead and say that really, at least in the back of your mind, you always want to be thinking that capital F is the rationals. I mean, it is useful to talk about other things. I mean, we will sort of talk about finite extensions of other fields, but including finite extensions of the rationals. That's a pretty natural one to think about. If things get a little confusing, you always want to think, okay, that base field is the rationals, and that's really what we end up being the motivation for all this. So suppose K is a finite extension of a field capital F, and that is in fact a splitting field. That is little f. This polynomial little f splits as into linear factors over K, and K is actually the minimal. Is actually the smallest possible field that could do that, because it's the field that you get by taking F and adjoining exactly the roots of those linear factors. The roots of those linear factors. That's right. So that you have to have those roots present in order to split f of x, because there they are. There's those have to be elements of K. But once you add those roots of little f, then a little f will split. Okay, so that's what it means for K to be a splitting field. We'll talk about that actually more on Wednesday, I think. Anyway, so the point is that Galois theory relates to field theoretic properties of K as an extension of F, like the degree, for one thing. We'll see a lot more than that. And the group theoretic properties of the group of field automorphisms of K that fix F. So those are, as we'll see, I think start to see on Wednesday, those are called Galois automorphisms, either on Wednesday or on Monday. As we shall see, these automorphisms must permute alpha 1 through alpha n, and they are therefore isomorphic to a transitive subgroup. Transitivity. If I say the word transitivity, thank you, Robbie, from earlier, that means that we actually have an irreducible polynomial. Not bad. Right. So that the transitivity comes from the irreducibility, comes from the irreducibility of f, and so the sort of signature problem, which you, if you've seen this before, you may remember, or you may have even heard of it, even if you've never seen this before. The signature problem of Galois theory is the question. I mean, there are other problems, but the sort of thing that got Galois excited and sort of made Galois famous for coming up with this theory is, when can those roots alpha 1 through alpha n be written as a function of the coefficients of f of x, an expression that uses only kth roots, square roots, cube roots, fourth roots, fifth roots, and that, in other words, when is there a generalization of the quadratic formula? If that's possible, then we say that the equation f of x equals 0 is solvable by radicals. That you can write down a solution. So the solutions to this equation using like using exactly. I'll put in a little meaningless doodle here. Square roots, cube roots. Can I actually write cube root? Oh, look at that. Fourth roots and so on. Just for, so that's our, there's the one slide summary of Galois theory. I always think about Austin Powers. Have you ever seen the movie Austin Powers? Wait, can I turn my camera on for this? I can't resist the temptation to be silly. Hello, YouTube. Where Austin Powers says, "Here's it in a nutshell. Help! I'm in a nutshell." All right. Sorry, YouTube. I apologize for doing that. Oh, you can see how long my hair is now. Isn't this crazy going for so long without haircuts? Gang, I will definitely have my man bun all developed by the time the semester is over. It's going to be very exciting. Anyway, sorry, what was I saying? Yeah, so here's where all of chapter 16 in a nutshell. But I want to emphasize that this is the overview of what we're doing. This is the 30,000-foot overview of what's going to happen. We haven't really really properly defined any of this, and certainly none of this is proven or solved. So none of these first few things are proven yet, and the last one has not been solved yet in terms of what we discussed. But the goal is to sort of understand all the stuff in this slide. And, well, in some ways, the easier part of this is is to sort of understand all these things, all the facts in this slide in the abstract. And then I think maybe the difference between what we're going to do here and what you may have seen in other courses is that we're actually going to apply it to actual examples. That's a total bear. Like, the theory is actually not that bad. It's all very pretty. The theory is like, okay to grasp. It's not easy, but it's relatively okay. But applying it to an actual polynomial, that is actually a hard part. As you may have seen in everything in this class, the hard part is to look at an actual example. Okay, so but are there any questions so far about this one slide summary of Galois theory, which we will see every day for the rest of the year, pretty much? Are you guys the right age to have seen Austin Powers? I can't tell. Maybe some of you are too young to have seen it. Maybe you're all too young to have seen it. Austin Powers? Yes? No? Trent has seen it. Trent, I feel like you and I maybe have similar tastes in things in some ways. Okay. I'm not sure I can exactly recommend it as a responsible authority figure, but I thought it was pretty funny. It's slightly naughty, I guess. Anyway, but it is pretty funny. Okay, right, so that's where we're going, and so let's now go back to the process of getting there, for which we have to do quite a different. Right, there's one convention we should work out just in case. Right. So today, the rest of today, the remaining 40 or so minutes, is going to be devoted to the preparatory stuff for Galois theory. The first thing of which is that I think it'll be. I'm not sure we actually at all really have to actually multiply any two permutations. God forbid we should multiply actual permutations. They'll take away my pure math license. But just in case, I want to be able to do that. So let me write out. Can somebody? That's something that people can do in the chat. Can two people type in some random permutations of like 6 things? So can somebody type in a random element of S6 in cycle form? Just stop. And don't worry, no one can see this on YouTube. So if you write something that's not I don't know, if you write something that's not a permutation, that's okay. 1, 2, 3. Thank you, Robbie. And I guess it's important to have something else that does not commute with alpha. Okay, 1, 4, 5. Thank you, Trent. 1, 4, 5, parens 2, 3. Okay, and so now, so the thing so the thing that always gets people, and I think actually in America, this is the usual convention. But I mention this because my advisor, my PhD advisor is British, and so he actually used a different convention, the British convention. So the convention used in Artin, and actually I think most American textbooks, is the left action convention. That permutations are written in cycle form and multiplied as left actions. They're sort of applied right to left, like you would apply functions. So alpha beta is really the sort of composition of two bijections. Alpha compose beta, which means you do beta first. All right, so let's see. Let me talk this through. Let me remind you, to multiply two permutations, you'll sort of see. So beta sends 1 to 4, and alpha sends 4 to 4. So this is 1, 4. And so as you may remember, the middle step was beta sends 1 to 4, and then alpha sends 4 to 4. And I guess the usual way that I like to say this is that 1 goes through 4. Let me type that out. So this is quote. That's fine. So the usual way I like to say this is that 1 goes through 4 to 4. So yeah, I'm not going to worry about this too much because I'm not sure we will actually have to do this in combat, so to speak. But is everybody good with that so far? So if you get that, and then the rest is, if you see what I mean by 1 goes through 4 to 4, that should really do it. Everybody okay? Any questions about that? Okay, I'll do the rest a little faster. So then let's see, alpha beta 4 goes through 5 to 5. 5 goes through 1 to 2. 2 goes through 3 to 1. Okay, so that closes off the first cycle. Let's see what's left. Oh, we only moved 1 through 5, so the only thing left is 3. And just to check, 3 goes through 2 to 3. And so 3 is a single cycle, which we could have left off. And so let me just put in one more example of this. 3 goes through 3 to 2 to 3. So make sense? Everybody good with that? Say yes, or ask a question. Yeah, so everybody go with that. Say yes or ask a question in the chat, please. Yes, says Mingru. Please, for the love of God, move on. Okay, so I just want to make sure that everybody, I think we made it. This may be the first and last time we multiply permutations in this class. Oh well, but just to make, I just want to make sure that, just in case that comes up later, because I actually haven't taught chapter 16 before, and just in case that comes up later, we'll have that. We'll all be using the same conventions. Okay. So let's look at elementary symmetric functions. So then now this is going to seem a little bit coming out of left field here, and I remember when I took this class out of this book, I think like right afterwards I mean this is like, I thought, well, A, this is pretty cool stuff, symmetric functions, and B, like, why did we do this? And the basic idea is that, and we'll sort of start to see why it is we're doing this a bit I think by the end of today. But you can sort of see already here. Let me sort of emphasize the point of this. So the reason we're interested in symmetric functions in section 16.1, as what we saw in the reading, is about symmetric functions. The reason we're interested in symmetric functions, and especially the elementary symmetric functions, the point is that the symmetric functions relate the roots of a polynomial to its coefficients. Or in fact, more precisely, as you can see here, by definition, they explain how the coefficients of a polynomial are composed from its roots. So so again, here's the definition. You can think of this as taking place in some sort of gigantic polynomial ring. I don't know. This is like, if you're feeling fussy, you could think of this as all taking place in the polynomial ring Z, bracket X, U1 to UN, if you like. Though, you can just think, I mean, I think it's actually literally symbol pushing, in a good way. So yeah, I guess that's what's going on here. It's Z bracket X, U1 to UN. And so we can define the elementary symmetric functions S1 through Sn as follows. Well, you take the product of all the polynomials x minus u sub I, as I runs from 1 to n, and you collect terms here. And as we know, this is a polynomial of degree n. So the first term of which is going to be x to the n, and then there's some other terms, and sort of it's not too hard to show by induction, for example, that the first term, S1, the coefficient of the x to the n minus, the negative of the coefficient x to the n minus 1 of the x to the n minus 1 term is just the sum of all the u's, u1 through un. The coefficient of the x to the n minus 2 term, the next term, is the sum of all the pairs of coefficients, u1, ui, uj, where I is less than j. This is just sort of, I mean, it's really I is not equal to j, but you don't want to double count anything, so I is less than j. So the correct sort of way to mark this formally is I is less than j. And S3 is all those triple terms, I, j, k, in that order. And so on down to, well, actually, the nth term is all the terms of the form u1, ui, uj, uk, where I mean, except there's n of them, but there's only one way to order n objects in order, and there it is. So these things are defined to be the elementary symmetric functions in the variables u sub I. Wow, this like kind of comes out of left field. I mean, yeah, I think maybe even legitimately this must seem like it comes out of left field. But again, let me emphasize that the point of this is that this is the point of the elementary symmetric functions. The elementary symmetric functions is that they relate the roots of a polynomial to its coefficients. Can I actually fix this here? So yeah. elementary symmetric functions relate the roots of a polynomial to its coefficients. So are there any questions about that, about this definition so far? Okay, so one sort of remarkable, notable property of each of these polynomials is that they are unchanged if you permute the indices 1 through n. So if you shuffle, I mean, that's sort of maybe easiest to see in the extremes. So if you, I mean, because this is just the sum of 1 through n, well, if you shuffle the indices, that doesn't change anything. Certainly, and because multiplication is commutative, if you shuffle the indices here, you don't change anything. It's maybe a little more challenging to see over here, but basically, these sort of middle terms are unchanged because all you're really doing here is you're collecting, and you don't really need this I is less than j. You just want exactly one term for every pair of element. What happens here is there's actually let me type this out. So for example, in S2, what's really happening is that there's exactly one monomial for each unordered pair I comma j. And because the set of unordered pairs is unchanged, and unordered triplets and unordered sets of 4, and so on, because those sets are unchanged if you permute the indices, well, all of these polynomials are invariant under permutations of indices. So does that make sense? Say yes in the chat or questions? No. Okay, good. Good to be honest. I mean, it's not good. It's not good that I'm like ranting incoherently, but Ravi, can you elaborate as to like what's going on here? Should I do a concrete example? Yes, please. Okay. So, okay, where's, oh yeah, page. It's been a while, huh? Okay. So, you forget how to do stuff. So let's see. So let's do example S2 for n equals 4. Yeah. So yeah. So for n equals 4, what does S2 look like? So so if you look at now, let me blow this up again. Yeah. So so as you can see, let me just copy this over. S2, by definition, is equal to the sum as over all I is less than j of ui uj. Actually, Ravi, so you were asking. Let me try to get one detail here. So does this first part make sense? That you multiply all these monomials together and you get some polynomial in x's and u's and the u's, and S1 is what goes with this term, and S2 does this first equation make sense, or should I talk about that? Yes, can I talk about that? Okay. All right. So so the question is, right, this is actually an old combinatorics problem. So if we, and let me put it this way. So it's helpful. I guess I'm kind of a visual person. So suppose we think about, by 3 I mean 4. Suppose we think about multiplying. So this is n equals 4. So we're multiplying. You're multiplying those 4 linear terms together, and you want to think about what. So what happens when you multiply these linear terms together? Well, for example, if you, in particular, if you look at the x squared term, you get x squared. So what you get is you get 2 to the 4th. When you take that product, you get 2 to the 4th monomials each. Yeah. So right. So what is combinatorics, right? So, or what actually? This is all sort of, if you guys ever teach sort of balls and boxes combinatorics or balls and boxes probability and statistics, I think the latter is highly probable. What happens? The reason that that's so difficult is that it's all about stories, and so you always want to say, like, when you have somebody solve a balls and boxes problem, you always want to ask them, what is the story that you're telling? And the story is that when you multiply these 4 linear polynomials together, you get 16 monomials each from choosing x or u sub I, from choosing x or u sub I in each line, each of these 4 lines, right? So again, when you multiply these 4 linear terms together, you get 16, a total of 16 monomial terms, and any one of those particular monomial terms comes from picking, like, say, x and u2 and x and u4. That gives you the let me illustrate that. So if you pick, for example, each from choosing either x or u sub I in each line of the product over there. So for example, what's one way to do that? So for example, one way to do that would be to pick x and then u2 and then x and then u4. And if you do that, that gets you to x squared times u2 times u4, which is u2 u4 x squared. So so everybody, does that make sense when I say that each of the 16 monomials comes from choosing either x or minus u sub I in each line of the product? Okay. All right. So yeah, Roby was happy with that, and so there's a cursor. All right. So in particular, the x squared terms come from choosing. I should have used an odd end, but oh well. This is good enough. Choosing x twice, as we see, and u sub I, one of the u sub i's twice. So each x squared term comes from a set of size 2. Let me say a set I comma j of size 2 inside the set of indices 1, 2, 3, 4. So So does that make sense? Okay. So I think we're in more in the ballpark here. So S2, that by definition S2 x squared is equal to well, like one way to get an x squared term is to have picked U2 and U4, but you could have also picked U1 and U2 and U1 and U3. You'll see pretty quickly why you usually don't write these out explicitly. Plus U1, U4, or you could have picked U2, U3, or you could have picked U2, U4 as we, oops. A little ahead of myself, over my skis there. U2, U4, U4 as we picked over there, and now U3, U4 times x squared. Sorry about that. It's a very messy 4 there. Anyway, so that's right. So what's really going on is that this is really what is really happening is what's really being enumerated here for S2 is the sets of size 2 inside the set 1, 2, 3, 4, and so and it's just that this is really this kind of mysterious way of writing this, maybe slightly mysterious way of writing this, is really just the sets, just way of specifying a sum over the sets of size 2 inside 1, 2, 3, 4. So does that make sense? Sort of pull back to the full page here. There we go. So does that make some sense? Everybody okay with that now? Okay. That's where that definition, that's what that definition means, and sort of where this slightly mysterious sum formula comes from. Okay. Oops, no. There we go. No, not full screen. Okay. All right. So those are the elementary symmetric functions. And so now let's sort of generalize that to looking at symmetric polynomials in general. So let capital R be a ring, and we note that permutations in Sn, permutations of n objects, act on the monomials of R bracket U1 to UN by permuting the indices, and so that action extends to all elements of R of bracket U1 to UN. So to say that f of U1 through UN is a symmetric polynomial means that f is fixed by every permutation in Sn. And so, for example, as we just saw, the elementary symmetric functions are all symmetric polynomials. So this is so this is a generalization of those elementary symmetric functions. So now, how should we do this? So I want to get let's see. So I want to get a random example of a symmetric polynomial in 3 variables. And so can somebody just type in maybe like a string? How about a string of length 4 in the alphabet 1, 2, 3? Just somebody give me something. Three, 3, 2, 4. Okay, so Trent typed in 3, 3, 2, 4, and so I will interpret that as so our seed for this is going to be so Trent typed in 3 twice, And so I'll take our seed for this to be x sub 3 squared, x sub 2, x sub, sorry, I'm going to change that to a 1. Actually, let me try that again. I meant 3 variables, so and somehow I said I meant 3 variables, and I somehow said 4 variables. So let me just slightly rewire that. So Trent, I'm going to take the liberty of changing your 4 to a 1, and so I'm going to make this x1, x2, x3 squared. Okay, and now if we act on that, if we now symmetrize this. Symmetrize, I haven't defined that yet, but you'll see what I mean after I do it. This by the action of S3. You guys did group actions last semester, right? Oh, say yes. Okay, if not, don't worry about it, but yes, okay, good. Yeah, I mean, there are people who do 221A without group actions, and oh, my gosh, it's just a different religion than me, but whatever. All right, so so what happens is, well, actually, yeah, since y'all did, so so the thing we're going to symmetrize by the action of S3 is exactly. Let me turn my pen back on. Is exactly this term here. Now, so what is the stabilizer of this term when I act on this by S3? Well, it's of course everything's stabilized by the identity, but also if I permute 1 and 2, if I have the transposition 1, 2, that will fix that polynomial, and so that means that the orbitous thing has at most 3 elements in it. Oh yeah, that's right. My favorite one of my favorite. Well, it's not just sort of one of my favorite theorems of all time. This is actually basically most of my research career is about the orbit stabilizer theorem. So orbit stabilizer in some generalized form, orbit stabilizer theorem rules. So the stabilizer, this thing has it turns out has 2 elements in it, the identity and the transposition 1, 2. And so S3 is order 6, and so the orbitous thing, orbit of this thing had better have 3 elements. And perhaps after a while you might see that you get those 3 elements by changing which term gets squared. So so I could square the variable 1, or I could square the variable 2, x2. And but now but if I have this thing here, this is a symmetric polynomial. Because this is now invariant under the action of S3. Well, just because any orbit is invariant under the action, any orbit under a group is invariant under the action of that group. That's the definition of orbit. Well, that follows from the definition of orbit. All right, so there's an example of a kind of random 3-variable symmetric polynomial. So good so far? Any questions? Okay, so we'll move on. So that is, I might have to do a more a trickier example later. Yeah, okay. Anyway, so right. So yeah, okay, well, that's fine. Well, we'll come back to that example later. So the main result of 16.1 is the symmetric functions theorem, which is a pretty neat theorem. And I'm pretty sure that wherever you did Galois theory, if you've done this before, you didn't do this at all. So you're like, what is he talking about? Why? But this actually, again, be patient. This will actually come in. The reason that this is useful is it's useful for examples and not for sort of the general. You don't actually need it for the general theory, but you do need it for example. It is very helpful for examples. So the symmetric functions theorem says that if G is a symmetric polynomial in the variables u1 through un, then G can be written, it's uniquely, but that's not so important, as a polynomial in the elementary symmetric functions s1 through sn. And the proof of this boils down to finding a systematic method for rewriting, doing exactly that, rewriting G, which we shall see in the next slide. So yeah, again, if we have okay, so let me actually point out what it's more interesting to look at examples. So here we have a symmetric polynomial, and yeah, actually, let me write that out. So for example, we had that symmetric polynomial s. I'll rewrite it slightly. Oops, I meant u1. I get my variables mixed up here. U1 squared, u2, u3 plus u1, u2 squared, u3 plus u1, u2, u3 squared. And now, so the point is that this, so the theorem claims that this should be, we should be able to express that as a polynomial in S1, which is U1 plus U2 plus U3, and S2, which is U1, U2 plus blah, 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 and S3 equals U1, U2 times U2, times U3. So, so the point, I mean, you might actually be able to see this, but let me, which I think means we might have to do a different example. Okay, maybe we'll just do this. And so, but okay. So the idea, so what the theorem says is that if I have a random symmetric polynomial, I should be able to rewrite it as a polynomial combination of S1, S2, and S3. And so there's our random example from before. I'll write it again. U1 squared, U2, U3 plus U1, U2 squared, U3 plus U1, U2, U3 squared. So the first thing we do is we set U3 equal to 0. And we get a symmetric polynomial G circ in 2 variables. Well, actually, the problem is here is that G circ equals 0. And so so step 2 is also sort of vacuous. G0 equals 0. And now the point is, you can show, this is part of the proof, is that when you subtract off, oops, and yeah, sorry, the point of that was we're going to find this new polynomial q, but q is actually also here the 0 polynomial, so it kind of hides what's going on. The point is, but the one thing you can see here is that is step 3. In step 3, we see that G minus Q, the original G minus Q is divisible by S3. So S3, remember S3 is U1, U2, U3, and lo and behold, this is actually divisible by U1, U2, U3. So it's equal to S3 times, when we divide that out, we get left over U1 plus U2 plus U3, which is equal to S3 times S1. Hey, well, that worked. That worked so far. Do I feel like doing, I guess I feel like, yeah, the corollary is not so hard to state. So let me actually try to do one more non-trivial example, a sort of slightly less easy example. Let me do G equals U1, U2 squared. Now this one, so this one here is actually going to have 6 terms, 3 squared plus U1, U, U2, U3 squared, but it's also the same things in a different order, switching to squared, U1 squared, U2 plus U1 squared, U3 plus U2 squared, U3. So there's a symmetric polynomial with 6 monomials in it. And so let me add in another page here. Whoa, sorry, sometimes my, okay, yeah, as you know, sometimes my renderer freaks out. So if we set U3 equals 0, then we get that G's, this polynomial G0. Well, if we wipe out all the terms of 3 in it, we get U1, U2 squared plus U1 squared U2, which is equal to, so this is equal, this factors as U1, U2 times U1 plus U2, which is equal to, which you think of as being S2 times S1, but in 2 variables. So the whole point of that Q is equal to S1, right? I should put a little circle here, S2, S1. And that little circle indicates that it's the U1 and the U2 in 2 variables and not in 3. So Q is equal to S2, S1. Or I guess I'll rewrite that as S1, S2. Okay, so that, which means that, we put that, when we translate that now into 3 variables, we get U1 plus U2 plus U3 times S2, which, oh goodness, which is that other thing, which is U1, U2 plus U1, U3, and 4 more terms. Okay. So, which means that G minus Q is, let's see, so what happens? So, let's see. Oh, yeah. So, sorry, let me just sort of quickly do this. You can just, so, there we go. So I guess I should actually multiply this out. Can you, those of you watching on YouTube, can you hear the flop sweat showing up here? Okay, so there's a bunch of UI, UJ squared terms. And that happens when each of these U1s hits something that already has a 1 in it. And there are, how many of those? There's, each one of those hits, 2 of those. So there's six of those terms. But is that right? Yeah, okay, sorry. There's only 9 terms to begin with. I just freaked out for no reason here. Okay, so there we go. This dot has only one thing in it. It's U2, U3. Whew, there we go. So there's 9 terms. So there's a bunch of UI, UJ terms. There's 6 of the terms. Plus U1, U2, U3, 3 times. So that's what Q is. So so that means that G minus Q is equal to minus 3 3, and actually, so when we look at those 6 terms of the form ui uj squared, this is exactly G. And so lo and behold, if we said gi minus q is equal to minus 3 u times u1, u2, u3, which is equal to minus 3 S3. So G is equal to S1, S2, minus 3, S3. Whew. Look, we did it. Only running 2 minutes over, just like old times. We're only running 2 minutes over. Okay, so so I think you might. So if that, so we run out of time. So I if that seemed difficult, you might want to just watch this last 10 minutes again on YouTube. But really, the thing you really got to do is to try this yourself at home. See Artin 16.1 for more examples. I think it's actually exactly this example, but you get the idea. All right. So so sorry about that. We got to give up as always. So nice talking to you, and we'll stop the recording now, and take care, and see you on Wednesday.